So let's do some practice. I guess this is number 81. This is, I'm slow, 8th edition. This is 8th edition Chemical Principles Zumdahl, which is the textbook we're using. So I'm simply, for the sake of the students and saving some time, putting them to sleep in class, if they're awake and at a moment of their leisure, could start practicing some of these balance the redox equations using the half reaction method. So let's see how well I can do with this. And I'm just starting up again, so this is going to start real slow for me. I don't have much time to practice this, so you can fast forward at will or whatever. And I'm just looking at the picture here. Maybe I can make this a little bigger. Okay. And again, it's this left-handedness that I have to rotate this stupid page in camera, so it's a little awkward. Okay. So the first step is you have to identify first what loses and what gains electrons. So the normal thing to do is you're going to look at this copper solid. It's neutral, so the oxidation number on that is 0. I'll jump over here. Copper, when it's by itself as an element and it's 2+, that charge, because this is by itself, that's a +2 oxidation number. Now, we talked about this in class a little bit right here. There are rules to assigning oxidation numbers. One method of finding the oxidation number of that is to use some memorized rules. So it goes something like this. We have 1 nitrogen plus 3 oxygens. I didn't want to make that look like 30. And that has to equal the charge on the polyatomic ion floating around, which is -1. The rules also tell us that unless you're stuck in a peroxide or something like that, oxygen pretty much always has a -2 charge. So that's a memorized rule. So this leaves us with 1 nitrogen, and we're going to solve for its oxidation number. This is going to be -6. Bring it over here, be a +6 with a -1. That is a +5. So we could use those simple rules we learned in nomenclature to assign +5 to that. We can use the other rules, which we used here, memorized, that oxygen, unless it's a weird compound, is -2. So these oxygens, and see how there's 3 of them? You don't add this up. You say, what does any one of these oxygens have as an oxidation number? It's -2. So this nitrogen over here, we could use the same rule. If that's a -2, then this has to be a +2. So what I'm going to do is illustrate again what I did in class. What would have been the second method? I call this the organic chemist style method, which is to get really up close and personal with the bonding. Now it turns out, in one of my other videos, NO3, we can look at this. We could start to apply another little trick, which is for oxy acids. If you put your 3 O's on a stick first, this is another memorized procedure for our bonding stuff. Hand out the negatives, we only have 1 to one of them, and we could double stick the remainder. But then a warning bell goes off, and the warning bell in bonding goes something like this. You have to spend the time carefully almost memorizing all these little exceptions, such as NO, NO2, NO3, N2O5, those types of things. So we know that nitrogen cannot make 5 sticks. So what we're going to do, a little bit of memorization, we're going to almost realize it's going to look like that. So part of this, so why do I want to draw this and find oxidation number organic style, and what does that mean? So if I know this is the structure, and there's other videos to explain that, let me redraw it. So I'm going to use little dots for the oxygen, and I'm going to use a little triangle. Why am I putting a triangle there? So So oxygen came to the party with 1, 2, 3, 4, 5, 6 dots. That would make it neutral, if you will, for accounting purposes of who is owning, technically like accounting, right, principles of the electrons. That negative becomes this oxygen over here. Normally it might make another stick, like an OH. Well, that's an extra electron. That's why it has a negative. We'll give nitrogen X's for its electrons. And we'll give this dots. And over here we'll give this dots. This oxygen comes to the party with 6 of its own electrons. Every single stick that is drawn in chemistry, 1 electron belongs, is the electron it brought to the party, shall we say, right? So every atom has to have an unpaired electron to make a stick. So this oxygen came with 6. This one has a formal, real charge of -1. That's what that extra electron is from. Nitrogen was supposed to come to the party, look at this, with 5. So this is you're witnessing it right now. Obviously, if this structure is correct, that nitrogen has lost 1 of its electrons. It only has 1, 2, 3, 4, 5. So it lost 1. That's why it has a formal charge on it. This has a formal charge because it has an extra electron. It doesn't have another stick. So now we would say this. This is where oxidation numbers in the molecule comes from. Look at this oxygen and nitrogen. Which one is more electronegative? Well, oxygen is. So what we do is, and I draw lines like this. Even though they think they're sharing this equally, or even partially unequally, like a bank account of money, and this is a relationship, the nitrogen and the oxygen, because they're the same bank account, they think they have equal ownership of it. But let's just pretend, almost like power of attorney, right? Power of finance papers. The more electronegative one gets that electron power of attorney. So technically, for accounting purposes, we can say this one basically controls this, really. So it's almost as if it stole it from here. So this oxygen formally has a negative charge, but it gains 1 more electron. So you can see why this one is a -2. This one, again, because oxygen is much more electronegativity, it's like it has the power of attorney over electrons in the bonds. So for accounting purposes of this relationship, I'm going to draw a line. For oxidation number assignment, we say this one technically owns these ones, even though they think they're sharing them. So this oxygen has gained 2 more, so even this one is a -2 oxidation number. This one has formally picked up an electron for real. So this is a real, actual negative charge. So that's a guarantee. But in the relationship between nitrogen and oxygen, this stick, this one, because it's more electronegative, has the power of attorney over that electron in the stick. So for accounting purposes, we say this one has a -1, but it gains another 1 for accounting purposes, and this is a -2 for that oxygen. So what's nitrogen's problem? It formally has a +1 charge. See how it's got 4 electrons it came to the party with, this party? It lost 1. So it already is at a +1. It lost ownership of this one, even though he might think, or she might think they own it. So that's another 1. It lost 2 more electrons, and it lost another 1. So that's a +5 for nitrogen. This is what I call the organic chemistry style of, specifically, we have to draw a Lewis structure of sorts, a Lewis notation drawing of sticks, and then we draw all the electrons in, and we account for who technically is owning the electrons in a bond, along with the formal charges that exist. So this is the ironclad way to do it, which helps out in organic chemistry, or you can use this method. So now where are we at? Back to the problem at hand. I meant to put this in on the front end just so people could see it. And fast forward if you want. So now we say, look, this copper, and my wording is, obviously it lost 2 electrons. And the nitrogen went from +5 to +2, so it obviously gained 3 electrons. Now we have to have that memorized words of oxidation and reduction. I still posit that in electrochemistry, if you yourself can categorically follow exactly what electrons were lost and what were gained, that right there is more than enough to answer any question. Technically, yes, we have to understand the nomenclature of oxidation. So what I do is I say, think about oxidation. The word oxidation itself, one of the classic things is you have a chunk of solid iron and you get some oxygen gas. And you'll make one of two things. And it's either FeO or Fe2O3. But the one thing we can see is in both cases here, both irons, this iron would be a +2 and this iron would be a +3. So either way you shake it, the action of oxygen gas on a metal is very obvious. We would say the iron was oxidized, the word coming from oxygen reacting with it, and we know that this thing that got oxidized lost electrons. So we could then say, okay, this is oxidation, this is reduction. There's many different memory aids for oxidation and reduction. What is it, Leo says GER or something like that? I don't like it. If all you needed to remember that a piece of solid iron and oxygen gas gives you something like this, and you follow the electrons, and you know what that word is, oxidation, it's pretty obvious what oxidation means, loss of electrons. So therefore reduction is just the opposite, which is gain. So what a lot of your books are going to say is they might even write down on the side, so the oxidation half reaction is this one, copper going to copper 2+. The reduction half reaction is NO3 negative going to NO, right? So now the steps are, look at this one. You have to balance the non-hydrogen and non-oxygen atoms. One copper here, one here, so that's good. The next point in the procedure says now you're supposed to balance any oxygens using water. Well, there's no oxygens in this one, so we don't even have to do that. The next step is we're supposed to balance, and in this question, but it doesn't really matter because even if you're in basic solution, you're told you always balance the acidic style first. So this one does say, if I'm correct, yeah, acidic. So we're in acidic solutions. The next step is you're supposed to balance hydrogens using H+. Well, there's no hydrogens here either. The very last step is simply balance the charge using electrons. So the right-hand side is at a +2. This is neutral. Well, if I add 2 electrons to this side, I now balance the charge. So we've completed the steps on that half reaction. So now we're going to move on to this one. Step 1. All non-oxygen, non-H atoms, which is nitrogen, are they equal? Yes, they are. So we're good. Next step. Balance oxygens using water. 3 oxygens here, 1 here. So therefore, I must add 2 waters. So now I have 2 oxygens plus this one. Oxygens are balanced. Next step. Now you must balance the H's by using H pluses, protons, because it's acidic. You've got 4 H's here, none over here. So I have to put in 4 H pluses. Next step. Balance the charge. This side is +4 and a -1. So the net is +3. This side's neutral. How do I make this balance? Well, I'm going to add 3 electrons to balance that +3 charge. Now that both half reactions have been balanced to this point, we now have to look at the combination of the two of them. The next step says the number of electrons in each of these half reactions. I call this the lowest common denominator approach. If you're adding a fraction of 1/2, 1/2 plus 1/3. How do you find the common denominator? Well, you're going to have to multiply this one by 2, so you get 2/6. This one's going to get multiplied by 3. Now you can add them. So when I say the common denominator approach, that's what you're going to be doing. So you need the number of electrons to be balanced. So I'm going to multiply this side by 3, and I'm going to multiply this side by 2. So I'm going to rewrite it A lot of people automatically put the 3 in now to save themselves steps, but I'm trying to illustrate what the result of this looks like. So you got 3 coppers plus 3 coppers plus 6 electrons. 4 times 2, that's 8 H pluses plus 2 NO3 minuses plus 6 electrons goes to 2 NOs plus 4 H2Os. You look at this being satisfied, you know those are going to cancel. So now you write down exactly what's on the left-hand side. Oops. Right? So 8H plus 2 NO3 minus plus 3 copper. And I'm just writing it in this way. I don't know if there's a specific preference. Is it like alphabetical C before N? I have no idea. NO plus 4. Now I guess what we're supposed to do is check that everything adds up. So how many H's are over here? There's 8. And 8. H's are good. How many nitrogens on this side? 2. 2. That's balanced. How many oxygens on this side? 6. 2 and 4, 6. That's good. 3 coppers, 3 coppers. And interestingly enough, you might think that the charge visually should be the same as over here, and that is not true. Or does it have to be? Let's check. 3 at 2 plus, maybe it does. I don't know. I've never actually bothered to look. That's kind of funny. 3 coppers at plus 2 is almost like there's a plus 6. Positive 8. Subtract 2 of these, plus 6. I guess even the charge balances. So that one's good. So that was 81A. Let's move on to 80. All right. See what we can do with this. So this is question 81B. See if this autofocus is going to stay where it should. Hopefully. So chromium. So chromium, you've got 2 chromiums plus 7 oxygens. Each oxygen is a -2 oxidation state. The charge on the whole thing is -2, so don't confuse that. And that is equal to -2, so 2 chromiums, that's a -14, bring it over, plus 12, so 1 chromium is plus 6. So this is a plus 6 chromium. Over here, it's obviously plus 3. Chlorine is -1 here, and elemental, chlorine is oxidation number of 0. So chlorine has undergone a loss of 1 electron. It's a lost one. So that's oxidation. The chromium has gained 3 electrons. And again, you want to make sure that some students still think that because there's 2 chromium, somehow there should be like 12 or something like that. That represents the charge on one of the individual chromium atoms itself. So we're doing it on an atom-to-atom basis. So we write out the this would be reduction. So for instance, the half reaction of reduction, you start out by saying you've got you got chromium 207. And that ends up as chromium 3 plus, and as far as oxidationville, Cl minus heads to Cl2. So the first step is you look at the number of, you don't look at oxygens and hydrogens yet. You always look at the non-hydrogen, non-oxygen elements. So you got 2 chromiums on this side, 1 over here, so therefore you need 2. Once that's done, and we'll keep with this one, you balance the number of oxygens with water molecules. 7 oxygens over here, I need 7 waters. So now the next one is balance the hydrogens using H+. You've got 14 H's. I need to put 14 H's, H pluses over here. Now you balance charge. So for charge, you've got 2 chromiums at +6. On this side, you've got 14 of these. Subtract 2. This is a +12. So you have to balance this using numbers of electrons. We have to drop this charge down. So I'd have to add 6 electrons so that this side overall is +6 and that's +6. So that looks good. We have to balance the non-oxygen, non-hydrogen numbers. 2 chlorines here, I need 2 here. No waters, no H's. Balance the charge using electrons. You have 2 of these, that's -2. Now it's -2, that's good. Now you have to balance the number of electrons being transferred. This is at 6, this is at 2. So all I have to do is multiply this by 3. So if I do that, I could rewrite this, rewrite both of them again just to illustrate. And a lot of books like to try and put it all on one side. It doesn't really matter. +6 electrons goes to 2 chromium 3+, +7 H2O. Multiply this by 3. Well, you got 6 Cl minuses. All right, let's finish this. We have 6 chlorines. 3 of those ones plus 6 electrons. 6 electrons cancel, and you're now left with +6 chlorines plus 14 H plus 3 Cl2 plus 2 Cr3 plus. So I think that's balanced. So of course you're going to check this. You've got 6 negatives plus 2 more, that's -8 plus 14, so you're at +6 on this side. This side has 2 at 3, you're at +6, so the charge balances. 6 chlorines, 6 chlorines, 2 chromiums, 2 chromiums, 14 H's, 14 H's. 7 O's, 7 there. So this is now balanced. So that looks good. And let's just see what else we have next. I closed the book. So now I got to refine the questions. So next, I start new. Looks like this is question 81C. And C looks like lead plus lead oxide plus H2SO4. And that goes to PbSO4. Okay. Interesting. So this lead is lead 0. This lead is lead 4? Lead 4 plus. Oxygen's obviously -2. And interesting. All of the lead ends up at lead +2. You can see how the sulfate and sulfate just sits there. It's a spectator. H2 doesn't seem to be getting oxidized or reduced at all. It'll show up in the balancing process for H pluses, right? So this is one of these tricky things. I remember when I was learning this, I'm thinking, what the heck is going on here? We almost forget that some of this lead goes to lead 2. Another source of lead also goes to lead 2, right? This one starts as 0, goes to +2. So this one was oxidized and it loses 2 electrons, but this one is gains 2 electrons. So it's almost as if it gains 2 electrons from here. Both of them become a lead +2 ion that hooks up with sulfate, and that's it. And this ends up becoming a solid, I'm sure, and it precipitates out of solution. So we have to almost trust the process and realize that some of the lead is a source of electrons giving up 2, creating lead +2. Another source of lead is +4 ion, and it gains 2 electrons, becoming lead +2. So they end up in the same sink, if you will. So if, I don't know, I write down, what's the reduction here? Reduction looks like lead oxide. Now what's interesting is it becomes lead sulfate. We have to include this, arguably, for both of them, because you get a sulfate. So the oxidation was this. Somehow it does interact with this at some point, because you're also making the lead sulfate, for sure. So follow the procedure now, which is we got to balance oxygen. So you've got 4, 5, 6. This only has 4. Did I balance everything but O's and H's? Lead was, so that's good. So we got to get 2 extra oxygens. So I got to add 2 waters. This side has 2 H's. This has 4. So we're missing H's. We need 2 more H's over here to get 4 to balance that. And once we've balanced that, we have to look at the charge. This is a +2. So we're going to have to add 2 electrons to this side to balance the charge. That's okay. This side, this is a lead and a lead, so that's fine. A sulfate and a sulfate is fine. Oxygens, 4 and 4, so the oxygens are balanced. This has 2 H's, so we have to get this side with 2 H pluses. Balance electrons, using electrons balance the charge. So it turns out these cancel, 2 H's cancel. So you're basically going to be left with a balanced equation already. 2H2SO4. And that gets you 2 lead sulfates plus 2H2O. So that looks okay. 2 leads, 2 leads, 2 sulfates, 2 sulfates, 4 H's, 4 here, 2 extra O's, 2 extra O's. So that's balanced. Looks good. So that one's okay. So then we can move on to, what do we got? D. So you've got manganese 2 plus sodium BiO3 going to bismuth 3 plus MnO4. If I copy that down right, this looks okay. So bismuth right here. You know, it's funny, when you take sodium BiO3 apart, you can get rid of the sodium. It's a counterion. So you pretty much know that it's BiO3 -1. So what is bismuth? I've got 1 plus 3 oxygens at -2 equaling -1. So 1 bismuth, that's a -6, bring it over, is a +5. Yeah. So this is a +5, and clearly it goes to a +3. So this thing gained 2 electrons. Manganese here is a +2. Manganese right there, you got 1 manganese plus 4 -2 oxygens equaling -1. So this is a -8, bring it over, it's going to be a +7. So that's a +7. So that obviously lost 5 electrons. So we could write out the two half reactions. You got manganese 2 plus becomes manganese O4 minus. Sodium BiO3 becomes Bi3 plus. So this one, manganeses are our balance. Next you go to oxygens. You're going to have to add 4 H2Os. That produces 8 H's. If I have 8 H's on this side, I balance it using H pluses on the other side, so that balances. Then we look at the charge. This side is at a +2 charge overall. The right-hand side is at -1 at a +7. I got to bring this charge down by adding 5 electrons. That one's good. This one says, look at the non-oxygen hydrogen stuff. Bismuth is fine, sodium is missing, so we would have to just add sodium. And then oxygens, 3 are here. I need 3 H2Os. Now I got to balance hydrogens. 6 hydrogens are on this side. I have to have 6 on the other side. Now this side is a +6. This side is +3, +4. So obviously this side needs 2 electrons to knock it down to +4 so that the charge on both sides is balanced. So this one's transferring 5, this is transferring 2, so now we're going to have to multiply this by 5, multiply this by 2. This is the common denominator effect, where the number of electrons being transferred has to be the same. So that 5 needs to turn into a 10 by multiplying by 2. This turns into a 10 by multiplying by 5. Let's rewrite it. The top one multiplied by 2 plus 8, and that goes to 2MnO4 negative plus 16H plus 10 electrons. Now 5 multiplies in, so you get 5 sodium BiO3 plus 5 times 6, that's 30 H pluses plus 10 electrons. 5 Bi3 pluses plus 5 sodium plus 15 H2O. Now we're going to add these two. So 10 electrons cancel. 16 of those turns this into 15. No, 14. 8 H2Os kills off 8 of those, leaving with 7. So now you're going to have 5 sodium BiO3 plus 2 Mn2 plus 14 H plus 2 MnO4 negative plus 5 Bi3 plus 5 sodium plus 7 H2O. And I think now we can look 5 sodiums, 5 Bi's, 15 oxygens, 15 oxygens. 8 plus 7 is 15. 2 manganese, 14 H's. Looks good. That one's good. So we've done that. What do we got next? We have E. Bring the focus back here. This camera. All right. So you've got H3ASO4 plus zinc. Keep looking at the book. I keep losing my spot. I don't know what I'm looking at. Zinc 2 plus. So is that right, Mike? What the heck? H3ASO4, you got zinc, you've got AS, H3, zinc 2. So again, we know zinc, clearly this is zinc 0, and it loses 2 electrons. What's arsenic doing? So arsenic over here, you've got 3 H's, which is always plus a 1, plus 1 arsenic, plus 4 times -2, and that equals 0. So you've got plus 3 minus 8 equals 0. So this is a negative 5. Bring it over. So this is right here. It's at plus 5. This arsenic, we know that hydrogen so where were we? We've got arsenic there. This arsenic looks like if you've got 3 H's, wow, arsenic. If these are plus 1s, then this should be minus 3? Now, I really am wondering about that. So, arsenic. Now I got to look at a periodic table. I don't memorize this, so I'm looking at a periodic table for some guidance here. What I'm wondering is that H going to be a hydride, where it magically steals the electron from here? That's what I'm wondering. And if it did, this would be a plus 3. So I'm kind of curious about that. Well, that's not much help, is it? So arsenic can be either plus or negative 3. So I got to be honest here, without looking it up, which I guess I could, what I'm going to do is I'm going to look at the electronegativity number, which its electronegativity is sitting at 2.1, and so is hydrogen's. So one of the other rules of debating, like if you have arsenic, H3, both H and arsenic are listed as an electronegativity. If you look in Berry's periodic table, the electronegativity number is sitting right below. So H is at 2.1, arsenic's at 2.1. So who's winning the battle of owning electrons? So, interesting. So my question is it a plus 3 or is it a negative 3? So I'm going to pause this for a minute, and I'm going to go check it out further. I really don't know. It's 50-50 here. All right, we're back in business again here. So had to go look online, and it turns out that this compound is listed at negative 3. Right? Yeah. So negative 3, my first guess was the way it's going to go. If we stick with the rule that H is pretty much always, most of the time, unless it's paired up with something like, for instance, sodium hydride, right? Then this one takes the electron. So here it's going to be a positive, 3 of them is positive 1 each, so that's going to be negative 3. So we could say that arsenic, holy smokes, from a plus 5, so that's gained 8 electrons. Wow, that's a lot. Okay, so we would say H3 arsenic, right, that goes to ASH3. Zinc heads to zinc 2 plus. So this one, arsenic looks good. Oxygens, there's 4, so you need 4 H2Os. This side has 8, 9, 10, 11. 11 H's. This has 3, so we need 8 more H pluses. Balance the charge. This needs 8 electrons to counteract that, to balance the charge on both sides. This one, zinc is fine, oxygen's fine, hydrogen's fine, so it's just electrons. 8 is transferred here, 2 here, we've got to make it common, so this one could be multiplied by 4. And it turns out, well, this one's easy because we're not multiplying them by anything. So basically I could just say 4, 4, 8. That cancels and you're left with H3ASO4 plus 4 zinc plus 8 H pluses. So let's check. 11 H's, 11 H's, 4 O's, 4 O's, 1 arsenic, 1 arsenic, 4 zinc, 4 zinc. Already did the H's. Looks good. F. Trying to blow through these here, just so you can see solutions played out in real time. I haven't even checked the back of the book if these are correct. So let's just go on a limb here and say that most of these let's just hope that most of these are correct. You know, and if you find that I made a mistake on some of these, we're just going to go with the story that this is part of the instructional process, that you know, I knew I made the mistake, just to see if any of you feed it back to me to indicate, oh yeah, you made a mistake. It's a check for sure to help instruct in a fuller, more complete way. You know I'm probably not telling the truth on that. Arsenic. You've got 3 oxygens, each of them at -2, so that's like a -6 total. And you've got 2 arsenics that have to equal +6, so this is a +3. Oxygen here is -2, these are -2, so that nitrogen, what's it doing? So NO3. We could say 3 -2 oxygens plus 1 nitrogen equaling a -1 charge overall. So -6 plus 1 N equals -N, bring it over, equals +5. +5 on that nitrogen. This arsenic, I think we can see, you could say I've got 3 +1s for the 3 hydrogens, plus 1 arsenic, plus 4 -2s, equaling 0. So you got +3 and -8. So this side is at -5. Bring it over. 1 arsenic is +5. This one, well, oxygen's -2. This is going to be +2 for nitrogen. So nitrogen goes +5 to +2. It's gained 3 electrons. Arsenic +3, so this gets oxidized, it loses 2 electrons. So the procedure says you set this up, the half reactions. That's an arrow, Mike. 3 arsenic O4. The other one is NO3 minus going to NO. So this one, 2 arsenics, you only got 1 here. This has to be a 2 to get 2 of those. Oxygen's next. 3 over here, 8 oxygens here. 3, 8. 3, 8. 5 H2Os. 10 hydrogens. 6. I need 4, 10, 6. 4 more H pluses. No charge here. +4. +4 electrons. You can see that makes sense anyway, because you've got 2 arsenics undergoing a loss of 2, so that makes sense for. Down here, 1 nitrogen, that's fine. 3 oxygens, only 2 here, so you need 2 H2Os. 4 H's, none over here, plus 4 H pluses. This side has no charge, this has a -1 plus 4, you're at +3. 3 electrons needs to be there. This is transferring 4, this is transferring 3. So we're going to have to multiply this by 3, multiply this one by 4, the common denominator sort of effect. So let's rewrite this just to show it. You're going to have 15 H2O plus 3 arsenic, 6 H3ASO4 plus 12 H pluses plus 12 E's. 4 gets multiplied in, you've got 12 electrons plus 4 NO3 minus plus 16 H plus, and it goes to 4 NO plus 8 H2O. Now, how many of you right now are saying, oh, why don't you just multiply it in now and change this graph? Why are you rewriting it? And if you feel that way or are thinking that way, you could metaphorically slap yourself a few times and say, why don't I take the extra step and show my work? It's just an option. If you think about it, killing off the 12 equal number of electrons transferred, this side is 16, that has 12, this gets killed off, this becomes 4. 15 and 8 goes away, 7. So you're going to be left with 3 arsenics, 4NO, plus 7H2O, plus 4H plus, goes to 6 H3ASO4 plus 4NO. I don't see anything else on that side. 6 arsenic. 6 arsenic. 9O plus 12. So oxygens. 9 plus 12 oxygen plus another 7. So you got 19 plus 9. That looks like 28 O's. 24 plus 4, 28. Guess that works. 4 N's. 4 N's. H's. 14 plus 4 is 18. 18. I guess we're done. Looks good. Where are we at? Page 81. No. Number 81. This is chapter 4. 81. I'm looking at G. I'm just trying to flatten these out. So you've got bromine plus manganate, and that makes bromine gas, or sorry, liquid, plus manganese 2 plus ion. So, okay. This manganese, you've got 1 manganese plus 4 oxygens, each at -2, equaling -1. So this is -8. Bring it over. This is plus 7 manganese. This bromine is obviously -1, and this goes to 0. So this goes. So if you're at -1 and you go to there, so you have lost 1 electron, the bromine. Now, as you get better at this, you can see obviously at some point you're going to need 2 of these for sure, because there's 2 over here. Each one of these 2 has lost an electron. Manganese went from +7 to. Did I already do this one? Like, am I duplicating this? Oh boy, if this is duplicated, oh well. Okay, it's been like 4 days. I'm supposed to get this done for the students hopefully by tomorrow, so they've got at least a week to watch some of these if they need it. So minus, no, +7 here, so you get 5 electrons gained. 5 electrons. So now we write these out. So you've got bromine going over to Br2. And then the other half reaction is manganate going to manganese 2 plus. Step number 1. Balance the non-oxygen, non-H atoms. 2 bromines, you need 2 of these. Second, balance oxygens using water. Well, there isn't any in this one. Balance H's using H pluses. Well, there isn't any. Balance the charge using electrons. Well, this is 2 minus. So obviously it's that. So that looks pretty benign. 1 manganese, 1 manganese. That's good. 4 oxygens. I need 4 H2Os. Balance the H's using H plus. So you've got 8 H pluses. Now this side is a +2. This is a +7. So you need 7 electrons. Wait a minute. This is plus 7, this is plus 2. The difference is 5. And I could tell up here, the way this is looking, 5 electrons. So a lot of times that number, or a multiple of it, will be what you need here, so you'll catch that. So that looks okay. So this is 2 electron transfer, this is 5. You have to make it equal. So we're going to have to multiply this by 2. We're going to have to multiply this by 5. This is like the common denominator sort of effect going on. It's almost like you have a 2 and a 5 for your denominator. The common denominator is going to be 10. So this will be 10 bromines goes to 5 Br2s plus 10 electrons. This one, 2 times 5 would be 10 electrons plus 2 MnO4s plus 16 H pluses, and that goes to 2 Mn2 plus 8 H2O. 10 electrons cancels, that's the same. And I think that's it. So you're going to get 10 Br minus plus 2 MnO4 minus plus 16 H plus, not plus, arrow, 5 Br2s plus 2 Mn2 pluses plus 8 H2O. Check. 10 bromines, 10 bromines. 2 Mns, 2 Mns. 8 O's, 8 O's. 16 H's, 16 H's. 2 negatives. And plus 16, you're at plus 14. Haha. Hello, forgot these. 10. Minus 10. So minus 12. So you're sitting at a plus 4, and that's at a plus 4, so we're good. It's got to work. So now we move on to H, which is methanol. Methanol aqueous, okay, that's fine. Methanol aqueous plus chromate, dichromate, I believe, dichromate, and that goes to CH2O, which is formaldehyde, plus chromium. 3 plus. So let's see, is that right? Yeah. Okay, so to figure this charge out, we already know that all these H's are going to be a plus 1. The O is minus 2. So part of how to do this is you almost need to know. So what is attached? Yeah, I can figure this out organic style. So the way I would do that is I would say this carbon comes to the party with 4 of its own electrons. Each hydrogen brings 1 of its own. So I could even extend this out in a stick. We'll use triangles. There's a triangle here. Oxygen comes with 1, 2, 3, 4, 5, 6. This comes with 4. But this carbon will steal in ownership, if you will, this. So this carbon will steal 3. So at the moment, it's sitting at a negative 3. But then it's going to lose 1 to that oxygen because that one's stronger within this stick. So that carbon is going to have, if it loses 1 of its electrons, that's almost like giving it a plus 1. So it's going to be sitting at a negative 2 oxidation state. Itself, right? Now, how would I... The other way we could have calculated is saying I've got 1 carbon, I've got 3, 4, in total I got 4 hydrogens at plus 1, and I've got 1 oxygen at -2 equaling 0. So 1 carbon, this is +4, and this is -2. This side would be +2 equals 0. 1 carbon equals -2. I guess that does work. And it's pretty obvious that I like the organic style method of accounting hands-on, all in front of me. This one works as well. So either way, that's a -2. So now you're over here. So we could say 1 carbon plus 2 hydrogens plus 1 oxygen is a -1 equals 0. So this is +2 minus, no, that's a -2. So this is looking like this is in a 0 oxidation state. Now what's funny is that structure of formaldehyde, if I do this organic style, looks like this. So the hydrogens come to the party with 1 carbon. This is what we're looking at. So this oxygen steals these 2, but then this carbon steals these 2. So it loses 2, gains 2, so it is 0. So carbon is now 0 over here. Chromium, you've got 2 chromiums plus 7 -2 oxygens equaling -2. So 2 chromium minus 14 equals this. 2 chromium equals +12. 1 chromium equals +6. So this is a +6 chromium. This one is +3. So obviously then, one of those chromiums gains 3 electrons, right? +6 to +3. Carbon goes from -2 to 0, so that lost 2 electrons. So then I'll start out, I'll see if I can sandwich it in here. So you've got this, and it goes to this. You've got dichromate going to that. So carbons, good. Next up, carbons is okay. Balance oxygens, that's good. H's gets balanced by H pluses. So you've got 4 H's here, 2 here. So you have to add 2 on this side. Then you balance the charge using electrons. This side's neutral. This side's +2. So I need to add 2 electrons on that side. Next up is this. 2 chromiums means I need 2 here. Next up is balance oxygens using H2O. Now you've got 14 H's on this side, so you got to balance over on this side, 14 H plus, and then we go to charge. -2, that's +14, so you're sitting at a +12 on this side. This side is at 2 +3, so this is a +6, so the difference is 6. You're going to take this down by 6 electrons. Yeah, which we already seen up here, 2 at 3, 2, it makes sense. So this is 2 electrons transferred, this is 6. Common denominator effect. If you had a 6 and a 2, you could say this could turn into 6 by simply multiplying by 3. Now since I don't have to do this one, what I'm going to do is I'm going to distribute the 3 in. So I'm going to put a 3 here, 3 here, 3 times 2, this becomes a 6, this becomes a 6. So these cancel. 6H pluses kill off 6 of these, so you're left with 8. So this looks good. So now we're left with chromate plus 3CH3OH plus 8 H pluses goes to 2 chromium 3 plus 3 CH2O. So let's check. 2 chromiums. Oxygens, you got 7 plus 3 is 10. 3 plus 7 is 10. Hydrogens. There's 4 here, 4 H's right here, but times 3, so that's 12. 12 plus 8 is 20 H's. This side has 14 plus 6. That's 20. Charge. Negative 2. Subtract 2 off 8, so you got a plus 6 on this side. Plus 6. We're good. So that completes the question 81, which was balancing everything in acidic conditions. So what I'm going to do is I'm going to move on to 82. So question 82 is about balance a whole bunch of things in basic. So what you do is you balance using H pluses like we just did. Then you go one step further by adding OHs to both sides. So let's do this. So you've got aluminum plus manganate or permanganate. Permanganate? I don't know. Manganese dioxide plus aluminum hydroxide. Balance in basic solution. All right. So aluminum here, right, for each OH is a -1. So you've got 1 aluminum plus 4, because this is OH minus, right here, 4 of them. So each at -1, and then you got equaling -1. Minus 5 equals -1. So that goes over and it's going to be a plus 4. So this is a plus 4 aluminum. This aluminum is 0, it's aluminum solid. Manganate, didn't we just do this? 1 manganese plus 4 -2 oxygens equaling -1. -8, bring it over, plus 7. This one, you've got 2, -2. Bring it over, this is going to be a plus 4. So this manganese gained 3 electrons. Aluminum has gone from 0 to plus 4. So it's lost 4 electrons. So that one gained 3, this lost 4. So something tells me some sort of common denominator thing will happen, but anyway. Manganate. And then you get aluminum. So this one's up. Number manganese, balanced. Balance oxygens using water. 4 over here, 2 here. I have to add 2 more. Balance hydrogens. This side has 4. So I'm going to have to add 4 H pluses on that side. Charge on this side, plus 4, minus 1. Plus 3, this side neutral. I got to balance it, so I better add 3 electrons to balance the charge. Aluminum. 1 aluminum, we're good. 4 oxygens. You got to add 4 waters for the oxygens on this side. Hydrogens on this side, you got 8. This has 4. I'm going to have to add 4 H pluses over here to balance the hydrogens. So now I get a neutral side. This is minus 1. I'm just looking at this for... Yep. So this one... Plus 4, so this is a plus 3. Neutral, so you got to add 3 electrons. So why does that seem like it's not adding up? One's gaining 4, one's doing that. There's a mistake right here. See, this is -4. Why don't you guys tell me? So that means this is a +3. So this, it has done 3. So you can see how this was taking care of it for me. Yep. Yeah, so you already have the number of electrons is already balanced. 4H pluses, that's dead. 2 H2Os kills off 2 of these. So balancing in acidic conditions, you would have So let's just do a quick check before we bounce to the basic conditions. 1 aluminum, 1 manganese, 1 manganese. Oxygens, you got 4, 5, 6. 4, 5, 6. Hydrogens, you got 4. 4. -1, -1. We're balanced. But it said balance under basic conditions. And what that means is you kill off any H pluses with OHs, but there's no H pluses. So this is kind of, there's nothing to do further. There's no H pluses present, so we're done this one. It's balanced, and it stays that way. So it's funny how in acidic conditions or basic conditions, this is going to balance the same. Unless I'm delusional. So that ends that one. So next up is chlorine. Didn't I do this one? Maybe I did it in class. I don't know. Chlorine gas goes to Cl minus plus ClO minus. So this chlorine is 0. This one is -1. This one is going to be 1 oxygen, Mike. -2 equals -1. This is a -2. So this is a +1. One of these chlorines, if you will, 0 to +1, means it lost 1 electron, whilst this one gains 1 electron. So you're going to get chlorine forming that. You get some other chlorine deciding to form that. So you need a 2 here. No oxygens, no H's. So therefore, balance the charge with electrons. 2 of those. You need 2 of these. 2 oxygens means you need 2 waters, which means you're going to get 4 H pluses over here. This is -2, the +4, this is +2. These are already there. So you're technically going to get 2H2O plus 2 chlorines. Gives us 2 Cl minuses plus 2 ClO minus plus 4 H plus. So aha, we've got H pluses left. Ah, I was hiding that in the camera. I wasn't paying attention. So the rules say kill off the H pluses by adding the required amount of base. But like a math equation, whatever you add to one side, you must add it to the other. And you need 4 of those, plus 4 OH minuses. This is going to make 4 H2Os. Notice you got 2 on this side, so this dies and this makes 2. So your final one for this is going to be 2 of these plus 4 OH minus Double check. 4 chlorines. 1, 2, 3, 4 chlorines. 4 oxygens. 2, 3, 4. 4 negatives. 2 of these, 4 negatives. So that's balanced. So this is balanced in basic conditions. So that's good. 3 more to go. C. So C NO2 minus plus aluminum goes to ammonia plus aluminum oxide. Well, a type of aluminum oxide. You got a negative. So that looks about right. This is 0. This aluminum, you got 1 aluminum plus 2 oxygens, H at -2, equaling overall -1. So 1 aluminum, that'll be -4, bring it over. So -1 plus 4 equals plus 3. So this is plus 3. So obviously that aluminum has lost 3 electrons. Now this nitrogen, each one of these gives up 1, so this is going to be a -3. And you can work that out. 1 nitrogen plus 3 plus 1 hydrogens equals 0. 1 nitrogen equals -3. This one you've got 1 nitrogen, 2 oxygens each at -2. So this is sitting at plus 3. So this has gained 6 electrons. So I would say this is a pretty strong oxidizing agent stealing electrons from this. Right? So you're going to get NO2 minus, NH3, so number of nitrogens is balanced, and you move to oxygens. 2 over here means you got to put 2 over here. Now this side has 4 plus 3, 7 hydrogens. So you got to put 7 hydrogens over here. Now you've got a -1 plus 7. This is a plus 6. That's neutral. 6 electrons is what you'll need. We could already see that. This one has 2 oxygens, so you've got to balance oxygens using H2O. Then 4 hydrogens puts 4 over here. That's neutral side. This side's plus 3, -1 and plus 4. So plus 3, right? 3 electrons. So this is at 6. This is already at 3. You only need to multiply this bottom one by 2. So why don't I multiply this by 2? That cancels. 7 kills off this to 1. 2 H2Os kills this off to 2. So we stop momentarily for 2 H2O plus 2 aluminum plus NO2 minus quick check. 2 aluminums, 2 aluminums, 2 O's, 3, 4. 4. H's, 4. 4. Charge, -1. -1. It's balanced there. We're balancing in basic conditions, so we got to kill this off with add to both sides 1 of those to make 1 H2O, but you're adding 1 OH negative to this side. So this one kills off 1 of those, so now you're left with H2O, 2 aluminum plus NO2 minus plus 1 OH negative. Two H's. Plus this one is 3. 3 H's. 1 oxygen. 2, 3, 4. 4. 2 aluminum, 2 aluminum. 1 N, 1 N. Negative 2, negative 2. Done. D. All right, we're back in business. D. So, we have MnO4 minus plus sulfur 2 minus manganese sulfide plus sulfur. So this is a 0. This manganese is a plus 2. This sulfur is a negative 2. This is a plus 7. So this goes gain 5. The sulfur loses 2. So we could have S2 goes to S. You could balance this right away. All you can mean, plus 2 electrons. MnO4 minus. Manganese good, but sulfur. So you have to balance with the source of sulfur in the equation to provide this one. So it'll be S2 minus. So now oxygens plus 4H2O. That's 8. 8. Now you're sitting at negative 3 plus 8. You're at a plus 5. So you're going to add 5 electrons. So I'm just going to try and save some time here. We're going to multiply this one by 5. So if I do that, this is 5, 5, 10. This one has to be multiplied by 2. 16, 10, 2, 8. 10 electrons, 10 electrons. So you're going to get 7s2 minus plus 2MnO4 minus plus 16H plus, and that would be 5s plus 2MnS plus 8H2O. 7 sulfurs, 2 manganese, 2. 8 oxygens, 16 of these. This is 7 times negative 2. So this is minus 14. 2 more, minus 16. This is neutral. This side's neutral, so we're good. We're balancing in basic solution, so we have to kill these off with 16 OH minus. Got to add it to both sides. This will make 16 H2Os, which will kill off 8 of those. So your answer looks like that. Last minute check. 7 sulfurs, 7, 2 manganese, 2 manganese, 8, 16 O's, 16 O's, 16 H's, 16 H's. This is minus 14, minus 2 more, minus 16, minus 16. That's good. So we're good for that one. And last but not least, cyanide plus MnO4 minus, which we've done this to death. So we know that manganese is going to be a plus 7. So we're going to CNO negative, and that would be plus manganese dioxide. Double checking that this is what it is. So that looks good. So in cyanide, oh boy, well, this is going to put me to the test. You know what's interesting? The cyanide, I already know, looks like that. So what's interesting here is nitrogen, I believe, is a little more electronegative, is it not? Nitrogen. Yeah, so nitrogen's supposed to steal ownership of those. So carbon loses 3 here, which would put it at +3 for the moment, but then it gains an extra 1. So this is sitting at a +2. Right? Now, C and O. So let's try this. 1 carbon. Yeah, see, I can't trust this. I really can't. So what I'm going to do, I'm going to rely a little bit on this. So how in the heck are we going to do this? Let me pause this. So I think you can see how I'm starting to form this. If I do this, and I'm just kind of talking out loud here, this is likely to be a +1. This would be neutral. Right? Lost 1. But when you do that, do you see how your carbon is waiting for this? So it's almost as if you would have to give it and be a -2. Another way you could draw this, and this is what they're claiming, if you give this a triple bond, leave this single, this is +1, this would be a -1, and this would be -1. 1, 2, 3, 4, 5. There's the extra electron. So if I'm drawing this picture, this carbon loses 3 electrons to this. So for the moment, the carbon is at a +3. But on this side, it's gained 1. So the carbon, and I think I just noticed what we're going to go back to that diagram. So this carbon looks like it's still a +2. Yeah. So nitrogen. We know that oxygen has stole that. Now this nitrogen stole these 3. So it's nitrogen's sitting at a +1 to start with. It's gained 3 electrons, so it's done that, but it's lost 1 more. So it's sitting at a -1. So that nitrogen is a -1. This is at -2, which is normal. So going back to what started this, I did the carbon thinking that was the one getting oxidized or reduced. That's a +2, but it's still the +2 here. This nitrogen gained 3, it's at a -3. So it's the nitrogen. The carbon was a +2. The nitrogen, wait a minute. Yeah, that negative belonged to the carbon, and I know it sits there. So the nitrogen is a -3. This is probably what makes it a little tricky. This carbon is still a +2. This nitrogen is a -1. And this manganese is a +4. Whew. Now, let's go back and try this one the old-fashioned way. If we trust memorizing some of these charges, well, this doesn't help. 2 ± 3, a 4, and a 5. Great! So, if I just take a stab at this nitrogen, see, how would you know, if you didn't know this, how would you know I got 1 carbon plus 1 nitrogen equaling -1? Well, carbon can be 2 plus 2 minus or -4. So I have to admit, other than memorizing it, this is the only way that I can come up with it. Now, maybe I'm just not thinking it through too fast, but this is where we're at. That nitrogen lost 2 electrons. This manganese gained 3 electrons. So we go Cn minus, and then we go manganese, permanganate. Carbon's good, nitrogen's good, oxygen's, this needs H2O, which means 2 H pluses. And then you have -1. This is +2. No, -1. This side, hold on, this side is sitting at +1. +2 subtract 1 is a +1. This is a -1 side. To balance them, you have to add electrons to one side or the other. So to make this to a -1, you got to add 2 electrons, which makes sense. This one we got to have 3. Manganese good, oxygen, there's 4, so you got to add 2 H2O, there's 4 H plus. This is a +3 side, that's neutral, so I need 3 electrons. So now we have to common denominator, 3 and a 2. This one gets multiplied by 3. 2 times 3 is 6. 6. This side gets multiplied by 2, so this is 8, 2, 2, 4. 3 H2Os brings this to 1. 6 H pluses, 8. So this goes down to 2. This is 3, so that times 2, that would have been 6. So we're left with 2H plus 3Cn minus plus 2 MnO4 minus, and that goes 3CnO plus 2 MnO2. Two H's, 3 carbons, 3 nitrogens, 2 manganese, 8 oxygens, 3, well there's 4, 7, 8, charge. Wow, 3 and 2, so that's -5 plus 2, so you're sitting at -3. This is -3. So we are good for balance in acidic conditions. This is supposed to be base, so we have to add 2 OH minuses to make 2 H2O. We add 2 OH minuses here. One of these kills off that. So the final answer, I believe, two H's. 8, 9. 4, 5, 6, 7, 8, 9 oxygens. 3 carbons, 3 nitrogens, 2 manganese. 3, 4, 5, -5, -5. We're good.